In this example, we're going to introduce two different concepts, one being equivalent systems, and then we're also going to be using part of that equivalent system to illustrate, that is, rather than something new, the concept of calculating moments. Right? So we've got two different blocks. We're going to talk about how we put them into a statical equivalency. Notice on the block on the left, let's call that system A, and then we'll call the other one system B, that they're both blocks are 5 inches by 8 inches. We've got a 50-pound force at the lower left corner acting up, a 30-pound force at the upper left acting to the right, a 10-pound force at the upper right corner acting down, and then a couple applied here at the lower right corner. Situation is sort of similar over on the left. We have but the number of forces and their magnitudes are changing, and the moment changes as well. Right, so we got 30-pound force acting downwards at the upper left. At the lower left, we have an upwards force of unknown magnitude, and then we have a 30-pound force to the right at the lower right, and a 100-inch-pound moment going in a clockwise or counterclockwise, that is, direction at the upper right. To have equivalent systems, what has to be true is that the sum of all the forces in a vector sense, well, that would be, say, the x direction, would have to be the same as all of the x components in the B system. Same thing with the y components. And ultimately, then the sum of the moments, let's take to the lower left as our point 0. Maybe that's convenient. And so for the systems to be statically equivalent, all three have to have this relationship of having equal translation, equal in both directions, as well as equal rotational effects. Right, so let's take a look here then. Right, sum of forces in the x in system A would look like we had a plus, let's take to the right positive, so a plus 30, and no other translational forces are there. If we go look at sum of forces in the x in the B system, now we have to take the same directions positive, but once again we have a plus 30 in the system, and they're the same, so therefore they're already equivalent. If we go then and look at the y, let's take upwards positive, we have a plus 50, minus 10. The rest of them don't have a vertical component, so that's a net, a positive 40. When we do this in system B, then we've got a minus 30 plus f, but that's it. Now we don't know what the magnitude of f is, but now when we equate these two, therefore that means that f must be equal to a plus 70 pounds, and it has to be acting up given the system that we have chosen here. Right, and then the last one is the rotational effect. Right, so now we're going to sum moments about point O. We could have done this anywhere, but I'm choosing to use it about point O. And let's take clockwise positive, because why not? Could have gone it the other way, it doesn't matter. I've got the 30 pounds times 5 inches, and then 10 pounds at 8 inches. Both of those are going clockwise. And then we have minus m. The 50 pound goes through the point, so that's going to have a 0 moment arm. So that'd be 150 positive plus 80 positive minus m. That's all in units of pound inches, or inch pound if you prefer, doesn't matter. We'll go to the other one and do the same thing. Point 0, the F force and the 30-pound force go through that point already. So then we'll have a minus 100 pound inches. And then, oh wow, look at that, the 30-pound force goes through there too. That's kind of interesting. So just means that, you know, when their line of action passes through the point of interest, then their moment arm is 0, and that's no point in even writing it down. So now we got one equation, one unknown for that one. And so we've got 230 here on with the 150 to the 80, take the 100 to the other side, take the m to the other side, and therefore we end up with that for statically equivalent systems, m would have to equal 330 pound-inches. Now, we've got to be real careful about the sign convention here. The positive just means that it's going in the direction that was shown on this free body diagram, which is a counterclockwise direction. Right? So those are the two forces necessary, F and M, in order to keep these things statically equivalent. Not in equilibrium. These things are accelerating, but nobody's told us that or required that. That's just simply the statement is that they have the same static effects on both.